Hi everybody. So today we're going to start chapter 4. So there are two parts: gray level modification, mainly for us to enhance contrast, and also image sharpening, mainly for us to enhance the edge. Okay. Right. So the main operations here is to modify the gray level. So we modify by means of mapping equations. So we map either linear or non-linear. But usually we will do a linear mapping. And so this mapping equation usually maps the originals to the what we want to modify. So the typical application is actually for contrast enhancement and also for features enhancement. So there are two primary operations. One is to compress and one is to stretch. So when we compress, actually we are reducing the contrast. So we actually do that when we are not interested in it. So we reduce the contrast. And then we increase the contrast by stretching the gray level, which belongs to where we want to see more details or want more info. So if you look at this mapping equation, so usually the x-axis is the original gray level, and then the y-axis is the modified gray level. So if you look at this slope here, where basically it actually, you can see the slope is greater than 1. So you can see that actually it mapped a small range from 28 to 75 to a bigger range from 28 to 255. So in this case, this range of gray level will be given more contrast. So, and the effect, if you look at it, so we know this, we want to see more details in this window. So we know that it actually belongs to this range of gray level, 2875, so we stretch it. And you can see that now the contrast of this window has been increased. And you can see more the texture of this window more clearly. All right. And in some of the cases, we may want to stretch a specific range, but clip the lower and the higher end, because we know that the very dark level and the bright level usually is not where something which we could see in details. So, but usually those in the middle is the one that we can more sensitive to. All right. So if you see in this case, the original gray level, so range from 050, we all map to 0. And the very bright level, 200 to 455, we map all to 255. So basically, we reduce the contrast in between these two range to 0. And the contrast actually will be given to from 50 to 200, we map to 0 to 255. So we practically increase the contrast of this range. And this is how the image looks like. So we can see now the dark now is actually you can't see much details, but now we give the contrast to the overall image. And we also have intensity slicing. So intensity slicing is we try to select a specific gray level which is of interest, and then we map to specific very high or bright value. So with that, we hope we could highlight the features of interest. All right. So if you look at this image here, so this line is basically returns the original image. But if you look at this, so we try to map particular range from 150 to 200, all map to 255. So, and you can see that the output actually is actually highlighting the features that we are looking for, in this case, the teeth. Or you can actually go to one extreme. Okay, you highlight only the teeth that you're interested in, and then the rest become dark. Okay, so our focus actually is on histogram modification. Histogram modification, here we are referring to the histogram of the gray level. So we want to know, we try to modify based on the gray level, the distribution of gray level, based on the number of pixels. Okay, so because with this information, we actually can tell which gray level is more important, and so on. So those, like for example, the face. So you can see the face actually occupied, quite a number of pixels here, the bright one, and also the hair, the dark part of it, another. So these are the important areas, important gray level, which based on this information, we can try to enhance the contrast accordingly. And so if you look at the histogram, those with small spread actually have low contrast, and histogram which is well spread actually has high contrast. All right. So basically, in order to enhance contrast, what we do is we try to either stretch or shrink the histogram, or we can also slide the histogram to increase the brightness or reduce the brightness. All right. Histogram stretch, increase, so therefore increase the contrast. And histogram strength reduce the range, and therefore reduce the contrast. Maybe you are wondering why we want to do reducing the histogram string to reduce the contrast. Now, when it comes to unsharp masking, one of the very famous image sharpening method, then you will see that this histogram string is actually one of the steps. And histogram slide for us to slide to the right, make it more bright. And when we shift it to the left, we actually make it darker. Okay, so this is the mapping equation for histogram stretch. So this is actually the original pixel values that you want to map. Okay, so this is the mapping. You minus with the minimum of the original image, and then you find the range of the original image by taking maximum minus minimum. And this is the new range that you want to map to, usually the maximum range. All right, if let's say 255, you want to maximize the range from 0 to 255. So this is 255 and this is 0. Okay, so this equation will stretch across the entire gray level range. And if you stretch, then you tend to have a better contrast. All right, next. Okay, so I'll show you an example. Okay, let's say this is the histogram stretch. This is the original image. So you want to stretch to full range of 0 to 255. So, right. This is the original image. So if you look at the maximum, it's 120. So the maximum of the original image 120. Minimum is 100. So we want to stretch to the full range, assuming 8 bits. So maximum 0, minimum maximum 255, minimum 0. So we use these equations. Okay. So just plug in the value. So we want to stretch 100. So let's see what we're going to map to for 100. So 100 minus minimum 100 divided by the range 120 minus 100, the original image range. And this is the new range, which typically the maximum range that we want to map to. So for 8 bits is 2550 plus with 0. So you get, so 100 minus 100, you get 0. So you get 0. And then when you stretch 120, so you take 120 minus 100, divide by the range and so on. So this one essentially is 1. So 1, so 255 minus 0 plus 0, so you get 255. So the new image, so 100 will map to 0, so all the 100 becomes 0, or 120 will map to 255. So now you can see that we have a line which is much brighter as compared to this, and the difference is much obvious now. But if you do that to some of the image, it may not work. Like for example, image we have some noise like this, where if you look at majority of the image, the histogram is very clustered. So clustered means very narrow. Why? Because you can see majority here is actually within this gray level. But if you observe in the histogram, actually, we have a very small majority of very dark pixels, which is this pixels here. and also majority very bright pixel, which are actually the noise. Okay, so if you try to perform ordinary histogram stretch on this kind of image, eventually because of the minority, so it will force the range to be spanned on the full range. Therefore, since when you stretch, you look for the minimum maximum, which is already 0 to 5, then you stretch from here, then you can't stretch anymore. So this is how it looks like if you try to stretch without clipping. I give you an example, a numerical example. For example, we have an image like this. So if you look at the majority, is actually between 100 to 120, but because of this noise here, the minority, 0 and 255. So if you perform histogram stretch, first you have to look for the minimum and maximum. And in this case, the minimum is 0 and the maximum is 255. And if you try to perform, then you're going to get, if you map 0, okay, so you find that your range of the original image is actually already to the full range 255 and 0. So because of that, then you find that it's actually quite difficult for you to stretch. You find 0 will eventually be mapped back to 0, 100 mapped to 100, 120, and you get back the original image, right? Now, in order to overcome this problem, what we can do is we can do histogram stretch with clipping, all right? So this is what actually happened when you do IM adjust. So they're going to clip the 3% low and high value. So when you clip the small percentage of the low and high value, so practically you're removing all this minority before you look for the minimum and the maximum. So after excluding them, then you will find the minimum and maximum here, which is the actual minimum maximum of the majority. Okay. So with that, then you'll be able to stretch the majority, the histogram of the majority, and therefore enhance the contrast. So let's say we try to perform histogram stretch with clipping. So in this image, so what you do is you need to sort and exclude the lowest and the highest. So in the example, previous one is 3%, but here, since we have so too few pixels, so I take 10%. So 10% of 9 pixels here is 0.9, so map to 1, round to 1. So so now we exclude one lowest and one highest pixel. So if you sort the whole image here, the pixel, so the lowest pixel, 1 pixel, and the highest 1 pixel, you can see we are practically ignoring this noise here. When we look, then only we look for the minimum and maximum. Okay, so now the minimum is 100 and the maximum is actually 120. Okay, so you see the effect of this excluding. So we exclude the noise, the minority, that forced to span the entire range. So now our maximum 120, minimum is 100. So you perform histogram stretch. So what happened to those values which is less than the minimum and maximum at 0, 2, 5, 5? So all those values which is less or equal, then we're going to clip. So anything less than the minimum will be clipped to 0, and anything above the maximum will be clipped at 255. And those in between then will perform histogram stretch using this minimum and maximum after we have exclude these extreme values. So you can see now we are able to actually enhance the image quite well. All right. So like what you have seen here. So that is histogram stretch with clipping, which is what the IM adjust does. All right. Okay. Next, we'll look at. I think we'll skip histogram string. Basically, the formula is the same, except now from a bigger range map to a smaller range. Okay. So when you reduce the range, then you can see that the contrast become poorer. Okay, and you're actually making the histogram become more narrow. Another one is sliding the histogram. So basically you add pixels with some value, either positive value or negative value. So if you add with some positive value, then the whole histogram will be slided to right and making the image become brighter. Okay. Right, now we're going to look at histogram equalization. So equalization is another very popular technique. It allows us to actually enhance contrast according to the histogram. So we can assign more contrast to those very dominant pixel gray level, which appear very frequently. So you can see that those that appears very frequent will be given more contrast. Those which is not so frequent will be given less contrast, okay, or even reduced contrast. So the basic idea is so that we can, because those gray levels that actually dominate the image should be very important part of the image, so should be given more contrast. All right, so let's look at how we actually do it. So first you need to have the histogram, okay, and next you need to do the run sum. Okay, run sum means, okay, we start with the first one, 10 plus 0, 10, and 10 plus 8, you get 18, and then 18 plus 9, 27, 27 plus 7, 29, and so on. Until here, 51, and then you normalize it by dividing with the total number of pixels, 51. And then this normalized value you multiply with 7. Why 7? Because in this case we are talking about 3 bits per pixel image, so the maximum is 7. And then you round it. So this is the new gray level. So 0 will be mapped to 1. According to this, 1 mapped to 2, 2 mapped to 4, and so on. All right. So that is about histogram equalization. All right. So for this, I'm going to show some look at the sample of questions. So we look at sample of question for histogram stretch in page 39. Okay, so you're given 3 bits per pixel. So this is your image. So explain briefly if given image is of good contrast. So actually this image has poor contrast. Why? Because for 3 bits per pixel image, you can have range from 0 to 7. If you look at this image, the range is only from 0 to 2. So it only occupies half of the range. So we can consider this as a poor image. So apply histogram stretch. So if you calculate the values, then you'll find that 0 will map to 0, 1 will map to 3.5, round to 4, and then 2 is actually the maximum map to the maximum of 7. And this is how the image looks like. And of course, in exam, you have to show the workings like what I show you here. Okay, you need to show the working. Okay, what is the maximum, minimum? What is the min, max, new max, and new min? Okay, and then you have to give a scenario where you want to perform histogram stretch with clipping. So you want to do a histogram stretch with clipping when most pixels falls within small range, but a small number of pixels, the minority, actually force the histogram to span through an entire range, which is something like this. Okay, actually majority have narrow range, but because of all this very bright and very dark, so now the histogram actually occupied the full range. All right, but majority actually occupied small range. Okay, so histogram equalizations. Again, given 3 bits, this is how the image looks like. So first questions, the above is considered low contrast. By looking at the pixel value, explain why consider low contrast. So then again, because it's 3 bits per pixel, so it should range from 0 to 7, but here you can see the range is only from 0 to 2, which occupies only half of the range. So one way is to perform histogram equalization. So, so this is how you should work out. So you have to calculate the pixels for all the gray levels. So 0, 5 pixels, 1, 10 pixels, and then 2 also 10 pixels, so total 25. So 5 by 5, 25, that's correct. So the rest all 0. So we perform run sum. So 5 plus 0, 5, 5 plus 10, 15, 15 plus 10, 25. All right. Oh, sorry, all this should be 25. There's a typo mistake here. Okay, next, divide by 25. So normalize it, and then multiply by 7. And round it, 1.4 round to 1. This one round to 4 and round to 7. So now all 0 will be mapped to 1. All the 1 will become 4. And all the 2 will map to 7. So always remember that you don't just give me the table. You have to also provide the final image after mapping. Okay. So sometimes an uneven contrast. Okay. So for these questions, I want to show you this one, which I have forgotten to do so. Okay. So like in adaptive filtering, we also have adaptive contrast enhancement. Again, adaptive means you will perform the contrast enhancement according to the sub-image. So this is an example of image where you have contrast unevenly distributed, meaning that some part have good contrast like here, some part has poor contrast. So this is what we call uneven contrast distribution. So with uneven contrast distribution, you can't apply equal enhancement to all parts. If you do that, then this is what you get. So we are going to need some kind of adaptive contrast enhancement. So if you look at this again, we're going to do like in MMSE, we are going to have window. So for each window, we're not going to calculate the variance, because variance actually indicates the contrast of the sub-image. So if the contrast is good, then you can see this ratio basically will turn to 0 and we'll get the mean. So meaning that we do not need to enhance the contrast. All right, and vice versa, if this is low, then you can see now this ratio become large, and we will actually boost the difference of the current pixels with the background, which is the mean. So actually you're getting the difference to add. So you're increasing the difference. So practically you're increasing the contrast of that particular window where the contrast is low. All right, so this is adaptive contrast enhancement. So this is the image where you have uneven contrast. So these are the steps, all right, when you do using different settings of adaptive contrast enhancement, all right. And so I want to compare what happens if you do adaptive and non-adaptive. This one, if you apply do histogram stretch equally across the whole image, so you find that the good contrast part now we lost the contrast. Okay, but here for this part of F, which is the one that you use adaptive contrast enhancement. Okay, so now you can see the contrast enhanced very well throughout the entire image. Okay, so coming back to this question, so if you have uneven contrast throughout the image, so what happens if you apply histogram equalization equally throughout the image? So then you will find that some image with good contrast may be over enhanced and region of poor contrast may be under enhanced like this. So those were really good contrast become over enhanced, now it become poor contrast. Okay, and to get better results you need adaptive. So briefly explain the concept. So the concept is actually enhance more in the region where contrast is poor. Histogram specification I have yet to cover, so I'm going to talk about histogram. Okay, maybe a histogram specification. You can go to the additional notes, and then you can go to histogram specification. Okay, so histogram specification allow us to modify image such that the histogram will near to the one that's specified by user. So in this way, then user can actually control the characteristic of our output image. All right, so the general step is actually to perform histogram equalization first on the input image, then followed by the histogram equalization on the targeted histogram. And then we link the two by using this link the step 1 to 2 to the nearest and the lowest. Okay, I think the best is we explain through example. Let's say now this is your image, and we need to modify so that the output histogram will be something like this. Okay, so okay, let's see how we do it. First, we take the input image. So this is the input image. Of course, then you have to count number of pixels for 0, where there are 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And then 9 pixel 1, grade level 1, 9 of them, and so on. So then you proceed to do equalization, where you actually calculate the probability, and then you calculate the run sum, 0.2, 0.2547, so on. And then you equalize the grade level multiply with 7. So 0.22 multiplied by 7 is 1.5, and so on. So this is the equalized version of equalization of input image histogram. Then you have to equalize the specified histogram, this one. So 0.25, 0.25, so you do the run sum, 0.25 plus 0, 0.25 plus 0.2505, and so on. Then multiply with 7. So, all right, so now it's the tricky part. So 0, okay, so for input image histogram is 1.5. So we look for the specified histogram, which one is the nearest. So 1.5 nearer to 1.75, but there are 2 of them. So we'll look for the lower one. Okay, always look for the nearest and the lowest. So if they are the similar, so we look at the lower one, so which is 0. So 0 will map to 0. Okay, now look at this, 3.3. So nearest will be 3.5. Okay, there are 3.5 here, which belongs to 2, 3, and 4, but we're going to map to the lowest. So 1 will map to 2. Okay, so 1 map to 2. Okay, what about 2? 2 equalized grade level here is 4.0. Again, 4.0 nearest to 3.5. So again, 2 will map back to itself 2. Okay. Next, 4. So equalized grade level is 4.8. So nearest to 5.25. 5.25 is under 5. So therefore, 3 will map to 5. 4, 5.4, first nearest to 5.25. So it's actually under 5. So 4 map to 5. And 5, 6. 6 will map to nearest 5.25. Again, 5 will map to 5. 6 is 6.8. 6.8 is nearest to 7. So 6 will map to 7. And 7, of course, will map back to 7. So then this is the output image. So 0 map to 0. 1 will map to 2. So all the 1 become 2. And the 2 also become 2. So all the 2 remains. And then 3 map to 5. So all the 3 become 5. And 4 map to 5. So all the 4 become 5. And then the 7, the 6 will map to 7. So 6 becomes 7. And 7 retain as 7. So all the 7 will remain. So now if you try to look at the histogram of this image, so now if you try to calculate the histogram, you'll find that the histogram is very close to what we are targeted, we have specified here. So this is histogram specification. Okay, and we look at the sample questions. So histogram specification. So again, first you need to come up with the histogram of this image. Okay, so calculate 0, 3, 1, 3, and so on. Then you do probability, and then you calculate the run sum, and then you find the histogram equalization, multiply by 7. Okay, and then you perform histogram on the specific histogram. This is a specified histogram. So 1/3, 1/3, 1/3, 0.33 running sum. And then the histogram equalization. So you multiply this run sum with 7. So this is what you get. So again, then you will try to map them. So 0.4 nearest map to 2.3. So 0 map to 0. And then 1.6 again, nearest to 0. So again map to 0. And then 2.5 again, nearest 2.33, the lowest, which is 0. So map to 0. And then if you look at 3.6, of course, closer to here, 4.6. So 3 will map to 3. 4.48, so 4.48 will be closer to 4.6. So again, 4 will be mapped to 3. Okay, even 5.3 is also very near the 4 closer to 4.6. So 5 will also be mapped to 3. 5 mapped to 3. Only when it comes to here, 6 is closer to 7. So 6 map to 7. And 7 will map to 7. And don't forget to give the final output. So that's histogram specification. Okay, here's example where you do a histogram stretch. So of course you have to show the working like what I did here. Okay, the mapping. You have to identify what's the minimum, maximum of the image. So in this case, the minimum is 0. Sorry, the minimum is 3. The maximum is 5. Then you do just plot. This one should be the new max is 7. New means 0. So plug in the value, then you will find that the lowest value 3 will be mapped to 0, and then the middle value 4 will be mapped to 4, and then the highest value 5 will map to 7. And equalization, as usual, you have to come up with the number of pixels by looking at the image. So 3, there are 8 3 here, 1 2 3 4, 1 2 3 4 5 6 7 8, and then 4 you have 8, 1 2 3 4 5 6 7 8, and so on. So then you do run sum, do normalization, divide by 25, and multiply by 7. So now 3 map to 2, 4 map to 4, 5 map to 7. All right. So don't forget to give the final output. Yeah. All right. So that is all for today. Thank you.